Very good. So let's start today. So today we will start with just presenting a few problems. So it is not, our aim is not to know how these problems are solved, but simply to know that there are special techniques for this kind of problem. So during this lecture of nonlinear optimization, we have seen a few techniques that are very general. And then we have seen specific problems, and this would be one of these kind of special families. So these kind of problems, they are called quadratic programming. So here you recognize a quadratic function. So you have the linear term. So this is the term of order 1. This is the term of order 2. So every time that you have x transpose some matrix x, so that is a quadratic term. And then the usual constraints that are inequalities and equalities. And what is special here to be called quadratic programming is that the matrix has to be symmetric, positive, and semi-definite. Okay, so positive semi-definite means if you have the matrix, and you compute the eigenvalues of this matrix. So you compute all the eigenvalues of this matrix. These ones are always larger or equal 0. So this is positive. So if it is only larger than 0, it is positive definite. And if you have the equal, then it is positive semi-definite. So it is all, so to be quadratic programming, the eigenvalues have to be larger or equal 0. And then there come constraints. These kind of problems appear in portfolio optimization. So portfolio is one of these in which you have multiple assets, each one with different returns. You want to maximize the return or to or here, to have a quadratic problem, you need to minimize the risk. So the risk is somehow associated to variance. So variance is a second order term. So minimizing variance, then you have this kind of quadratic terms. Support vector machines that we have you studied support vector machine? Yeah. So there you also have a quadratic programming problem. In model predictive control is we have a system. So you have a system with some input. We have some course on linear systems or signals and systems, something like that. Yeah. Okay. So you have a system, and you want this y as a function of t, for instance, to be stabilized along some line. So you want this one to be stabilized along that line. And then this is control. The control problem is when you want the output of a system to behave in some particular way. And the one that we have here is model predictive, is because you want to predict how the model will behave in order to control this. Okay, if this is positive semi-definite, this is this symbol here, then the problem is convex. And now you know from all convex problems, they have a unique solution, and it can be relatively easily solved. And that can be done with some of the techniques we have seen, interior points, for instance, we have seen active sets, we have not. But if this is not a positive semi-definite, then the problem becomes non-convex. Then you have all the problems associated to non-convex optimization. That is, it has multiple local minima. It depends on where you start. This is positive semi-definite. Okay, so if Q is not positive semi-definite, then you have a non-complex problem that is NP hard to solve and so on. So that is fine. Then different kind of related problems, they are called these ones second order cone programming. So second order cone programming, it is a generalization of the previous one with cone constraints. So now this is the equation of a cone. So the equation of a cone involves somehow this matrix A is kind of rotation of the cone, and then this somehow determines the radius and the aperture of the cone. And then you want to minimize some linear function subject that the solution is in this cone. Yeah, so dA defines the rotation, and the C here controls the aperture of the cone. And yeah, here you have a few problems in which these kind of problems appear, this kind of families appear. So whenever you have a constraint that applies to the norm of your vector, or when you do quadratic programming in a robust way, in some special cases of portfolio optimization, in lasso, when it is formulated as a quadratic programming problem. Then semi-definite programming. So semi-definite programming is another family. And here what we want to minimize is the trace of X. X now is a matrix. And then you want to minimize X with some linear transformation. And then you want to minimize the trace of that subject to some other constraints. This is the way of expressing linear constraints now with matrices. So, and X has to be positive semi-definite. And again, this appears in control problems, in combinatorial problems like this MaxCat or coloring algorithm. MaxCat we saw no? With when we had the graph problems, we saw the MaxCat problem. No? Otherwise, I'm sure we can find some nice picture of this. MaxCat graph problem. So the MaxCat is, okay, so I have a graph and I want to find, so it is connected and I want to find a cat between, to generate two subgraphs such that the weight of this cat is maximum. Okay, so that is what we want to solve. And it is an NP-hard problem, so it is one of these combinatorial problems. And then anything related to covariance, not anything, but when you want to estimate the covariance matrix, also you have this constraint. And here you see that this kind of problems is very well suited for covariance matrices, because the covariance matrix has to be positive semi-definite always. Okay. Then you have this conic programming. So conic programming is looks like a linear programming problem. So this is minimization of a linear function, but subject to some rotation or some transformation of X belongs to a cone. So it belongs to a convex cone. And this convex cone, for instance, can be the positive organ. So positive organ, 3 dimensions. I can, so let's say you have a vector. So you have a vector R, Rn, and then the positive order is, I don't know how to call it, but is all the points such that x1, x2, all of them are larger than 0. So it is this octa. Okay. Then when you have a second order cone or a positive semi-definite cone, And somehow this phonic programming is a unified framework for the other problems we have seen today. And they can be solved with these primal dual interior point methods that we have seen. And this is the summary of these kind of problems, how the objective function looks like, and then which are the kind of constraints we have, and some examples of problems when they appear. Any question? Linear, this is linear programming. That is the one that we saw at the beginning. Any question? No? So we don't see the general techniques normally can solve these problems, but also there are some specific techniques especially suited for them. Okay, so with this we finish the lecture on non-linear programming, and what I would like now is to show you some of the applications of these tools. So they appear, for instance, in many what they are called. Okay, so let's say optimal design of materials and structures. So, for instance, you want some chemistry lab, you want to minimize the stress of a material and the non-linear elastic constraints. So the materials are elastic, and then you want to design a structure such that it minimizes the stress while it keeps some elastic constraints. For instance, in non-linear model fitting, so when you have to do a curve fitting, for instance, in pharmacokinetics, I think that we have a figure here. So let's say that this is the behavior of the concentration of the drug in blood when you take a pill, for instance. So this is time. So you take the pill at time equals 0. And then at the beginning, you don't have any drug in blood. But then it starts dissolving and being absorbed. And then the concentration of the drug increases. And then at some point, so you're constantly degrading that and secreting that drug, so eliminating it from your body. And then it starts, after most of the pill has been absorbed, the concentration starts decreasing, and then it is completely eliminated by some time. So this is a non-linear function, and you have to feed this non-linear function to a number of observations. So for instance, this appears in pharmacokinetics, but it can appear in any scientific domain in which you have observations that behave in a non-linear way. So this non-linear optimization makes a lot of sense. We'll come back to this formulation later again. So curve fitting in pharmacokinetics, systems biology, and this is a very broad family of problems called inverse problems. So an inverse problem, it refers to, so you have some input to a system, then this operator of this system transforms this input into an output. And this is called the forward problem. And then the inverse problem is the opposite. So you observe the output of a system, and you try to figure out what was the input of that system. Okay, and that most of these inverse problems, they are formulated in this way. So you have F will be your operator. So you have an input X, you excite the system in some particular way, and then the system will respond. And you have to find the input to that system, or even the system itself. And then the output of the system has to be similar to the output you have observed. That is the meaning of this. And this term typically is called the data fidelity term. And then very typically they are regularized. We already know what regularization means. We have seen most of the important regularizers. Here you have a summary of them. And so, for instance, these L1 norm of X, you know that it promotes sparsity, or even the L1 norm of the derivative of X, or some Bayesian priors or whatever. And here you have another inverse problem, for instance. So let's say that you have, here, this example is taken from structural biology. So let's say that you have a protein or a molecule, and then you put it into the electron microscope, and then the electron microscope generates images. You can have a lot of these images, and you know for which angles or from which angles you have taken each one of the pictures, and then you have to invert the problem. So the forward problem is I put the molecule in, the microscope will generate a projection. The inverse problem is I have a set of projections, which was the molecule. Okay, so, and all of them, they are formulated in this way. So here again, you have the formulation of this nonlinear fitting problem. So this is a very typical structure. So you have the data fidelity term plus the regularization. So the system or the input to the system has to behave in some particular way that is somehow encoded by this regularization. For instance, in robotics, it also appears these nonlinear problems. So in robotics, let's say that you have a number of obstacles, and you have some robotic arm that has some joints, and then you have to define which is the path that, for instance, it is minimizing this thing. So it is. So here we have the velocity and the acceleration. So the velocity, so you have for every, so you will describe, where is it? Yeah. So this Q is what you can control. So you are minimizing with respect to Q, and this Q is the angles that these joints can take. Okay. So you can control those angles. Those angles have to be within some ranges because all the joints have some particular maximum and minimum angles. They will start some positions. So they will start in some position Q0, and they have to finish at the end of your sequence. They have to finish in some particular positions. And then what you want so you will go from the initial to the final positions in number of segments, and these segments in capital N segments. Each one of them, these are time segments. So each one of these time segments, you have N joints. So you have to control the N joints, and you want to minimize along these time segments. What you want to minimize is the norm of the velocity and the norm of the acceleration. And you can measure the velocity and the acceleration in these ways. So you recognize approximations to the derivatives. And what is the meaning of this? So this is, so you want to penalize, to minimize this, because this is penalizing jerky motion. So the acceleration, if you have changes in the acceleration, it is moving very quickly and then stopping and then moving quickly again. So you want to avoid that. And high energy use. So high energy is encoded by velocity squared. As you know, it is an energetic term. So this is a function that you want to minimize. And then your control variables, the ones that you can modify, are the joints and how the joints change over a segment, some time segments. Okay, so this is one problem. Here you have these trajectory optimizations in general, and now you understand more or less how they look like. This model predictive control, for instance, there are systems that are designed to maintain, for instance, this inverse pendulum. Do you know the inverse pendulum problem? So it is like when you take a broom here and you try to maintain it straight. So this is the inverse. This is again a control problem. or nonlinear state estimation. So nonlinear state, this is another family of problems. Sorry. That is very interesting. That is, this system has some internal state. This is the state of the system that you cannot observe. All you observe is the input, you observe the output, but you cannot observe the internal state of the system. And then you try to estimate the internal state. There are a number of algorithms. One of the most known ones is this Kalman filter. So the Kalman filter tries to estimate what is the internal state of the system. Then neural networks, everything, we will have next lecture is on neural networks, and everything is defined as an optimization problem of some loss function with respect to the weights of the neurons. And then that is non-convex. It is a non-convex optimization problem, non-linear, and very often you do it in a stochastic level. And this adaptive optimization, you already know what it is. It is adapting the learning rate and the step sizes to the norm of the gradient. Then you also have, for instance, in neural networks, you have some parameters that behave in a discrete way. So, for instance, the number of hidden units, the number of layers, or the size of the filters, or all that, or the batch size. So all these are discrete variables, and you already know some discrete optimization algorithms, and some others behave in a continuous way. So, for instance, the learning rate, the regularization coefficient, the dropout rate, these are continuous numbers. But all of them together, they are called, in general, hyperparameters. So the parameters, typically, they refer to the weights of the neurons, and the hyperparameters to all these other things that they affect the output and the behavior of the network, but they are not all parameters. Then reinforcement learning that you saw actually last year with me, I think. So reinforcement learning, it was another, it is another kind of problems where the goal function to minimize is non-linear, and you use this kind of techniques. So in general, the formulation can be formulated this way. That is, we want to find the hyperparameter vector that has d dimensions that minimizes some validation loss. So actually, this is interesting. You don't want to minimize the training loss. So the training loss is for the parameters, and the hyperparameters focus on the validation. Yeah, and the problem with this goal function is that it is often very noisy, non-smooth, is expensive to evaluate. So you can imagine that for every combination of parameters, hyperparameters that you want, you have to minimize, or you have to train a full neural network. So that is very, very expensive to do. And because this is a non-linear optimization, you can be tracked into local minima. So from the point of view of the hyperparameters, this function f behaves in a very kind of a stochastic way. Signal processing and image processing, they're full of non-linear optimization. And here we have compressed sensing. Compressed sensing, we already said, we already explained what it was. So it is, you have a signal. So you have a signal, let's say, which is time. So time, have the signal. And we are familiar with this regular sampling, but you could also sample in a stochastic way. So you put random samples, so one sample here, another one very close, I have one here and one there. So the spacing between samples is random. And then how from these random samples I can recover the original signal. And it turns out that from the random samples, typically you need fewer samples than from the regular sampling. So this is very interesting. But then, so because I have to measure fewer times, but then the problem is how do I reconstruct the original signal? And this is the goal function of compression, and it is a nonlinear optimization problem. Phase retrieval appears the Fourier transform. Do you know what the Fourier transform is? Okay, so there are many devices that record the amplitude of the Fourier transform of the signal, but cannot recover it. And for instance, X-ray crystallography is one of those. So X-ray, let's look for X-ray diffraction. So you have a crystal. A crystal is nothing more than a regular repetition of some molecule. And then you have diffraction patterns that may look like these ones, for instance. So, and this is the amplitude of the Fourier transform, but you have lost the phase. And then there are many techniques trying to recover the phase. And those techniques, again, they are nonlinear optimization problems. Blind deconvolution. Blind deconvolution is, all these problems are very nice. They are very nice. So, how does it change? So this one is, you have an ideal image, but this is what you observe. And then this is the true PSF, but you don't know. And then the problem is try to estimate the original image and the point spread function of the system. So the system has degraded the original image in some particular way, such that this is what you observe. So can I estimate what is the response of the system and what was the original input? And this is the blind deconvolution problem. So blind because I don't know what the point spread function is. Okay. So this blind deconvolution, super resolution is very nice. Super resolution. So super resolution is this. So for instance, this is not computation, okay? This is by hardware. So you design the microscope in a different way, but the problem is kind of similar. So you recover a low resolution version of some image, and then you want to have the high resolution version of it. So when you blur this one, you get this one. And this is a super resolution problem. And again, this appears in all kinds of imaging. Very good. Then cryo-EM. Cryo-EM is actually what we do at the lab in CSE. In my lab, what we do is this cryo-EM. Cryo-EM is cryo-electron microscopy. So it is, you want to know what is the structure of a protein, and then you prepare a solution of that protein, you put it in the microscope. This microscope illuminates with electrons rather than with photons. and it generates this kind of images. Each one of these small dots is one of those proteins, and then you have to, for instance, this one, you collect all the images that are seen the molecules from the same orientation. So some of them are top views, some of them are side views, or any orientation with respect to this one. Then you collect all those that are similar, and then you have 2D class averages that are cleaner. And then the general problem is, from all these observations, can I recover a map of the molecule that is compatible with these measurements? So I have a map that is 3D object, have to project it. For each image, I have to project it into a different orientation, have to convolve it with the point spread function of the microscope. And then this one should look like this one, except for the noise. And actually, you recognize this difference, a square norm is attached to the concept that the noise is Gaussian and independent from, so the noise on one pixel is independent from the others. So all these kind of norms assumes independent Gaussian noise. And then you have a visualization on the map. And then you recover from these images, you recover these maps. In biology, you also have this kind of optimizations, where you have some observations of the concentration, for instance, of some species, chemical species, and you know how you have a culture of, I don't know, of bacteria of a particular kind. You have put certain concentrations of nutrients, and then you see, you observe what is the production of some metabolites or some whatever. So these are the metabolites that you are observing. This is your input, the nutrients that you have put, and you have made, for instance, multiple observations over time, and you know that the transformation from nutrients to these output chemicals, they are controlled by these chemical networks, if you want. So these chemical reactions, they can be defined by differential equations. And by start with some initial condition, you can simulate forward how these chemical reactions will behave. And so you try different parameters for the different reactions, so different speeds. And you at the end, you want to minimize the difference between what you predict and your observations. And in that way, so the parameters are the different speeds. So in that way, you can estimate what are the speed parameters of each one of the reactions that you are looking at. And these so this parameter estimation in nonlinear biochemical networks, so this one, a different one that somehow it is also related, it is this drug scheduling. So I can simulate what will be the response of the system to some drug scheduling treatment. And radiation planning. So when you have radiotherapy, you have to control how much energy you emit and with which frequencies from different sources, and which is the geometry of these sources. And you have somehow to minimize the dispersion. See if I find some nice picture of this radiation planning. So somehow here it is somehow illustrated. So let's say that you want the combination of all those forces to be maximum in some region and minimum outside. So this is the kind of nonlinear optimization problem that you would be solving. Let's say that you have some magnetic resonance imaging from the brain or some electroencephalograms signals, and then from this output, you want to infer what is the brain connectivity, so how the different neuron fibers are connected. Then in finance and economics, again, many optimization problems, maximize utility with some production subject to some risk constraints, and these risk constraints are nonlinear, or maximize a non-linear function of the portfolio, or some modeling how the economy of different countries behave. So this is macroeconomy. And for instance, here it is this guy Markowitz was a Nobel Prize in economy, and it was on portfolio theory. That the problem, this is a simplified version of this problem, but somehow it is minimize the variance of your portfolio. Variance, you recognize here a second order term, and try to maximize the return. And here you recognize, okay, minimizing something that is possible, but I want to maximize this, so I will subtract, so change the sign, because I want to maximize this term. And then that gives you, if you have here a plot of what is the volatility is this variance, and the return, the expected return. So you want to minimize the volatility, but at the same time maximize the return. And then there are some trajectories that are optimal in this space. And then more applications here. So each one of those use somehow nonlinear optimization. So nonlinear optimization, we have seen many tools because they appear in many real life problems. And now you know how to solve them. Very good toolkit. That's all. Any questions? No? Then we stop here, and